So, welcome to session number 6 of module 1, wherein we are discussing about stress and strain in the materials. So, until now we have seen how to calculate stresses and strain in the bars or rods subjected to tensile and compressive loads, and with the different materials, and also with different kinds of loading at the different points on the material, on the bars. So next we'll discuss about composite bars, or what is called as compound bars. So there are some structural applications wherein we make different structural members by combining minimum two or more materials. So while combining two or more materials, what happens is different metals, they have different properties, and each property, particular property of the material is used for structural applications. For example, if you take RCC, the civil structure RCC, reinforced concrete cement. So here in that we use steel bars which take the load, and the concrete, it covers the steel bars and transfers the loads to the steel bars. So like that, there are many structural applications where we combine two or more materials, and that combination of the bars or the materials is called as, the structure is called as compound bar or composite bars. So here you can see a composite bar here, the sectional view, and this is the side view, and we have inside a solid bar, and outside it is enveloped, covered with an hollow bar. So, and these two are made up of different materials, and usually when the materials differ, their properties, particularly stiffness or Young's modulus, also differ. So based on the applications, we use different materials so that we can transfer the load to particular bar or particular material, and other one is used to cover that, or maybe for aesthetic views, or maybe for some other applications or some other usages where the particular load is transferred to the material which is designed to take the loads. So in that cases we combine two or more materials or bars, and we get the compound or composite bars. So here one thing you have to understand here is that the structural member or the structure made with the composite bars, when the load is applied, they undergo the same amount of strain, that is delta L. So both the materials will undergo same amount of strain. They are designed to undergo same amount of strain or change in length. So obviously when the strain has to be same, and the modulus of elasticity of the materials is different, so the load or stress in both the materials will be different depending on the load taken by the one of the bar in the composite bars. So here we will calculate, or we will understand how to calculate stresses in the composite bar. So here we have taken a composite bar wherein we have a hollow tube, which inside which we are having a solid bar. So the two different materials are there for solid bar and hollow bar, and these are the dimensions specified here, and this is the length of the bars, compound bar, and the load applied is P here, and that is the tensile load is applied, and both ends are fixed here. You can see the ends are fixed, and if the end is not fixed, then when the load is applied, both that is the composite bar will undergo a strain or elongation of delta L. So in that case, as I told you, when the metal property changes, when the Young's modulus changes, and when the strain is same, the loads or load carried by different materials in the composite bar will be different, and therefore stresses developed in both the materials will be different. So here you can see we'll analyze now, wherein we'll take the extension of the composite bar. This is L is the composite bar length, and delta L is delta L be the extension or elongation of the composite bar with when the load is applied. So we will take ES and EH. That E is the Young's modulus, S is for solid, and H is for hollow bar. So similarly, we take sigma stress in the solid bar and stress in the hollow bar, and we have this particular equation. So this relationship we develop is because of this. So the main criteria here, equation of compatibility, is that delta L, change in length in the bar, should be same. So using that, change in length of the solid bar should be equal to change in length of the hollow bar. So the change in length formula, PL by AE or sigma L by E. So you apply that for both solid and hollow cases, and we take the equation in terms of stress in the solid bar. So stress in the solid bar is expressed in terms of stress in the hollow bar, and you can see we have the Young's modulus for both the materials of the bar different here, and we will calculate the area as such. So area of the hollow bar and solid bar, the formula is there, and we take so here we can calculate. So since the stresses are different, so obviously the loads applied or load carried by each member or each bar in that composite bar will be different. So coming to load carried by the hollow bar with respect to stress, we have the formula: stress is equal to load by area. So load on the hollow bar is equal to stress in the hollow bar into area. Similarly, for solid bar, again load will be stress into area. So here one more relationship is that the total load what we apply, the total load what is applied on the bar will be a summation of the load carried by the solid bar and the hollow bar. So that relationship you have to use, and we will get the total load P is equal to PS plus PH. So this is the load carried by the solid bar, and this is the load carried by the hollow bar. So substituting the values here for the loads in terms of stresses, we will get this equation, and since the stress in the hollow bar is expressed in terms of stress in the solid bar, that is substituted here, and we will get this relationship here. So this is the load applied on the composite bar, and how that load is shared by both the solid and hollow bar with respect to the stress in the solid bar and with respect to stress in the hollow bar. So here we have an example. We will solve a problem here with a composite bar. We have its a cross section is given. So it is one material or one bar in the composite bar is made up of steel, and other one is made up of aluminum alloy. So both are flats. So flat in the sense we have the cross section will be rectangular. So it's not a circular cross section, it is a rectangular cross section. Flat means it's a long bar, and the cross section will be rectangular or square. So here I think it is given as rectangular, wide and thickness. So it is rectangular cross section. So by looking at the geometry or the cross sections, we should decide whether the bar is circular or rectangular or square or whatever it is. So you should analyze the problem when the statement is given. So here we have a flat bar of steel. So a steel flat bar is there. We can see the front view and the sectional view, side view, sectional view here. So this is the front view, and we have the cross section AA. So at this cross section AA, this is the alignment or arrangement of the two bars. So the steel flat is in the middle, and it is covered by the aluminum flats at the two ends, bottom and top here. and this is the length of the bar. So, and load is applied, which is given here 20 kilonewton. So tensile load is applied 20 kilonewton, and you can see here all the three flats are there, 2 and 3. So one is made up of steel and other two are aluminum flats, and they are fastened together at the ends. And the Young's modulus of steel is given, Young's modulus of aluminum is given. So using this data, what you have to find out? You have to find out the stresses developed in steel and aluminum. So here, since the two ends are fixed, that is all the members in the composite bars are fastened and fixed together, when the load is applied, the change in length or the strain should be same. So when the strain is same, obviously, as I told you, the stresses developed in the metal will be different, because the two materials will have different modulus of elasticity. So here first we'll calculate the cross-sectional areas as usual, because the cross-section is given, dimensions are given, so we can calculate the areas first. So here we have the upper steel flat and the bottom aluminum flat and upper aluminum flat. The thickness is 9 millimeter and the width is 24 millimeter. So you can see 24 millimeter width is there for both the aluminum and steel flats, but the steel flat is 6 mm thick, steel is 6 mm thick, and the aluminum flats, they are 9 mm thick. So cross section is same, that is width is same 24 mm, but thickness is different for steel and for aluminum flats. So this is the cross section. So once we know the cross section geometry, we can easily calculate the area, cross sectional area of the steel flats and the aluminum flats. So that same in the derivation we saw that the condition is that the strain, that is the change in length of the composite bar, should be equal for both the members or both the bars of the composite bar. So this is steel bar and this is aluminum bar. So both the aluminum and steel bars or flats should extend by same quantity or by same amount. So delta L for steel should be equal to delta L for aluminum. So change in length for steel should be equal to change in length for aluminum. So using that formula, that condition, PL by change in length is PL by AE or sigma L by E. So this is length of the members, both the members is same, so keep it common here, whereas stress in the steel is different and Young's modulus in the steel is different compared to stress in aluminum and Young's modulus in aluminum. So using this relationship, we will express sigma x in terms of sigma A. So here L and L length is common, so Young's modulus that is given. So we establish relationship between sigma s and sigma A. So if you substitute the values of epsilon x, that is modulus of elasticity of steel and aluminum, and if you substitute the values, you will get sigma s is equal to 3 times sigma A. So you can see here the stress in steel is 3 times the stress in aluminum, because the modulus of steel is higher than the modulus of aluminum. So the load carried by steel is more than the load carried by aluminum. So the stress in the steel will be more than the stress in the aluminum. So that understanding you can get it by seeing at this equation. And also one more condition is that the load, whatever your load is applied, that will be shared by aluminum and steel flats. So the load applied is equal to load shared by solid, that is steel flat, and load taken by the aluminum flat. So the load taken by solid, that is steel shaft or steel flat, is expressed in terms of stress in the steel flat. So load is equal to stress into area. That formula you can apply here, and again if you substitute the values, so if you sigma s is nothing but 3 times sigma A. So now I am expressing P in terms of sigma A. So you have only one term here, sigma A, and remaining they are all areas. So now we have equation P is equal to sigma A 3AS plus AA. That is, the P value is known, sigma A you have to calculate, and area of the steel is known, area of the aluminium is known. So you can easily find out the stress in aluminium. Okay, so stress in the aluminium we can just calculate by this formula. Just substitute the values, you will get it as 23.15 megapascal. Just take the value P and areas. Similarly, when the aluminium stress in the aluminium is known, by using this relationship we can calculate the stress in steel. So this is the stress in steel, 3 times the stress in aluminium. We have one more applications of composite bars. So I told you about RCC, or what is called as columns. So even in columns or in some structures, we have the concrete inside, and it is covered by the steel. Just imagine some columns in the civil structures. So here the steel is covered, steel covers the concrete area. So here the load taken by steel is different and the load taken by concrete is different. So here also we have, so this is particularly the application of what is called as post. So post in the sense, usually they are used in making pillars on the roadside, for example, for mounting the street lights or something like that. We make poles, or what is called as posts, to carry higher loads. So you might have seen on the roadside or in the some circles, to mast eye mast lights, we have the headlights. Okay, to support those headlights, we make the steel structures, vertical steel structures, which hold the load of that floodlights or any other lights. So they are called as posts or the masts. So here we have a post or a column which is made by steel plates. So we have the steel plates on either side. It's a square cross section, 200 millimeter by 200 millimeter, and inside the steel column, it is filled with a concrete to give the strength. So here the steel square is 200 mm by 200 mm. Thickness of the steel is given as 10 mm. So you can see thickness of the steel is 10 mm. So you can calculate the area of this steel, cross-sectional area of the steel material here, cross section. And the stress in the steel is given, the allowable stress or the design stress is given as 140 megapascal, and the stress in the concrete should be not more than 12 megapascal. So in this problem, the stresses are given, and you have to calculate the safe compressive load on the post. So you have to calculate how much load can be applied on the post or on the column. So here it is just like unlike the previous problem, the load was given and we calculated the stresses. In this problem, the stresses are given and we will calculate the load here. But the equations remain same, the same equations we have to use, and same conditions will follow. And using those equations, conditions, we will try to find out the load P, which can be applied on this structure. So the first condition is the strain or elongation in both the steel and concrete should be same. So using this, we get the relationship between what is called as sigma S and sigma C. So sigma S, stress in the steel, is equal to 10 times stress in the concrete. So in that case, already the stresses are given. the stresses are given here, but using this equation we will see whether it satisfies the condition or not. So in this case, when you assume that the sigma s is given as 140, when you substitute that sigma s in this equation, what will happen to sigma c? Sigma c is 14 Newton per millimeter square. So actually the stress given, the stress, allowable stress in the concrete is 12 Newton per millimeter square. But when I use this equation and when I take sigma s as 140, what will happen here? The stress, allowable stress on the concrete is 14 megapascal, which is more than 12 megapascal. Therefore, this condition is not satisfied. So the assumed load or assumed stress is not safe. So what we do is, we assume that sigma c is 12. We take the vice versa, other case, sigma c will take 12 and we will recheck this one. So when I put sigma c as 12 megapascal, what will be sigma s, that we'll see. So when I put sigma c as 12, what will happen to sigma s? Sigma s will be 120 megapascal. So it is given that the stress on steel should be, the allowable stress should be 140 megapascal or below 140 megapascal. So when I use this stress in the concrete, the stress in the steel will be 120, which is less than the allowable stress or design stress. So that means I can consider sigma c as 12 megapascal and I can consider sigma s as 120 pascal. So he has given the limit here. So the steel stress should not exceed, the stress in the steel should not exceed 140 megapascal. But in my condition, when I put sigma c and calculate sigma s, it is well below 140 megapascal. So it is below. Stress in the steel is applicable, only 120 megapascal is applicable. So it is very much, it is well below the limit permissible stress given in the problem. So I can use this equation, this relationship here. Now if I use sigma s as 120, then it is safe. So the load what we calculate, it will be safer load. So once the stresses are known, to know the to understand or to know the value of loads, we should know the areas, cross-sectional areas of that cross sections of the bar, steel or concrete here. So area of the concrete section, you can calculate what is the area of this. So it is a square here. So if this is 200, the thickness of the steel is 10 by 10 here, 10 and 10. So this will be the length of this concrete will be 200 minus 10 minus 10, so 180. So the length, it's a square. So the concrete is a square now of length 180 by 180. So area of the square will be 180 by 180. Similarly, area of steel tube will be, we would calculate the area of steel tube, that is, so area of steel tube, what we do is we take the length as 200 mm and if you minus this area, you get the area of the steel. So area of steel, cross-sectional area of the steel is nothing but the area of this outer section minus area of this cross-sectional area of this concrete. So if you remove this much area, you will get the area of this steel. So total area 200 into 200 minus area of the concrete, that will give you the area of the steel. So once we know the areas of the steel and concrete and the stresses in concrete and steel, it will be easy for us to calculate the load. So total load is nothing but load on concrete plus load on steel. So load on concrete is expressed in terms of stress here, stress into area. Similarly for steel, stress into area. So if we add both the loads on both the members, it will be equal to the load on the structure or the composite bar. So just substitute the values, you will get the load as 1300 kilonewton. So this much load you can apply on the post or on the column so that it will not fail. So here we have one more problem wherein again we have a load of 500 Newton suspended using the two rods or bars. One is made up of steel, other one is made up of copper. Diameter of this steel bar is given, so it is a circular bar, and this is a circular, this is also circular, 2.5 mm diameter. So just imagine wires, steel wire and copper wire are used to carry this load, and the two ends of the wires are fixed here. So there are some applications, structural applications, where the load will be suspended or carried by these two wires. So in such case, how do we design this structure, or how do we find the stresses or the loads on these materials, and how do you design this particular structure that is there, that you have to calculate. So in this problem you can see the load is 100 Newton, and the load is suspended by using two wires made up of steel and copper, and both the wires are circular in cross section because diameter is given. And you can see that 500 Newton is not in the center, but it is at some distance x from this end. So it is given here. A load of 500 Newton is suspended on the rigid bar such that the rigid bar remains horizontal. So you should be careful here to understand that since we are using two different wires to hold this load, the load of 500 Newton will not be, if it is in center, then what will happen is the stresses or load carried by each will be different. So that we will understand now. So the load or the center of the gravity of that particular load should be at distance x. So it is given the distance between the wires as 150 mm, and is telling us to determine, so this is important, we should understand or we should find out the location of line of application load. As I told you, this load will not be in the center. So line of application of load will be some distance x from A. We'll assume that it is at some distance x from A. So this load is not applied at the center here. Always remember, because if the load is applied at the center, since these two are of different materials, then the load will be twisted. So these bars will be twisted along at this fixation here. That we'll see later when we analyze. So here, what is important here is we have to find out at what distance the load should be applied, or the line of action of the application of the load should be at what distance should be there from A. So remember that this is not in the middle now. This 500 Newton, the line of application of this load is not in the middle of 150 mm. So it should be at some distance, it should be offset at some distance at a distance of x from A. So that you have to calculate. And also you have to calculate the stresses in each material, that is each wire. So obviously the modulus of the two different, since the materials are different, modulus will be different, modulus of elasticity will be different, and also stresses will be different. But one thing is that the strain, that is elongation of the two wires, should be same. That is a condition. And Young's modulus is given in terms of ratio here. So Young's modulus of steel is so much here, and Young's modulus of steel is 3 times Young's modulus of copper. That is given. That relationship is given. Anyway, we'll use this. So this is the given data. So first in the problem, another problem is given. Try to analyze the problem and try to draw the diagram of that problem. So whatever statement is given, that statement you have to express in terms of a diagram or a schematic diagram. So when you read the statement, you should be able to draw this. So usually in the examination they may not give this diagram. They will be giving only the statement, problem statement. So you have to read the statement problem correctly, understand it, and you have to draw the diagram according to the statement. So once you draw the diagram, it will be easy for you to analyze, understand, right? So first we will calculate the areas of the copper wire and steel wire. So since the diameters of the steel wire and copper wire is same, the cross areas of the copper wire and steel wire will be same. Calculate that, and since the elongation of both the wires will be same, that condition you apply here, and you can express stress in steel with respect to stress in copper. So the relationship between, that is, Young's modulus of steel and copper is given. So what will happen, sigma s will be 3 times sigma in copper. That's the one condition. Other condition is the total load applied is sum of the loads on steel and copper. So these two conditions you have to use. So one condition is the strain or elongation of the wires or the compound bar is same for both the materials. Other condition is that the load applied on the bar or on the compound bar will be equal to the sum of the load on each member or each wires here. So in that case, what we do is we apply this formula, both the conditions. So from first condition, if elongation is same in both the metals, we get this condition, sigma s is equal to 3 times sigma u. And again, in the by the second condition, the load applied on the bar, composite bar, will be equal to load in the steel plus load in the copper wire. So this is another second condition. So using this equation, now we will write the loads in terms of stresses. So when you write the loads and stresses in terms of loads for both the steel and copper, we get this equation. So here we have P is equal to sigma s AS plus sigma C copper, and since we know the relationship between sigma s and sigma u, substitute that and we will get this equation. So P is equal to sigma copper 3 times AS plus A C copper, that is Cu is copper. So here this equation P is equal to expressed in terms of stress in copper. So and the area of steel and copper is known, and load P is known here. So what will be getting? We will be getting the stress in copper. So first we will get the stress in copper as 25 megapascal. So when you get the stress in copper 25 megapascal, you come back to this equation, substitute copper stress value of copper, and you will get the stress in steel. So sigma s is nothing but we will get 3 times of sigma Cu. So stress in copper into 3 will give the stress in steel. So using these two equations, we can find out the stresses in copper as well as in steel wires. Now we will find out the elongation. So next that is important here. So here what is important here is the downward movement of rigid bar is equal to elongation of wires. That is, the rigid bar will move down, or it will move down. That will be equal to elongation of the wires. So elongation of the wires, or the elongation or the movement or the displacement of the rigid bar or the weight. So how much this weight displaces or moves down, that it depends upon, that is equal to the elongation of wires. So here we have the formula for elongation of wires. We know that it will be same for both the wires. So either you can use PL by AE for steel or PL by AE for copper. So here we will calculate the downward movement or displacement of the rigid bar or the weight, this weight here. So that will be equal to the elongation of the wires. So you can use steel or copper here. So steel, the stress in steel just now you found out. Then Young's modulus of steel is given, length of the wire is also given. So this length is given 1.2 meters. Substitute that, and this is the, so you can see here the weight or the rigid bar will move downwards by 0.456 mm. And here we have to find out the position of the line of action of the loads here. So position of the load on the rigid bar is computed by equating moments of forces carried by steel and the copper wires about the point of application of load on the rigid bar. So here what is important here is, so we will take the moments about this steel bar and the copper wire here. So if you take that moments here, so we have the load on steel into X. So the load taken by, that is the load taken by the steel wire into distance X, that moment should be equal to load taken by the copper wire into this distance to maintain equilibrium. So the load taken by the steel into X is equal to load taken by copper, and the distance is 150 minus X. So this is 150, this is X, so this will be 150 minus X. So that if you take the moments about this point, they should be equal, and when we equate that, we get the value of X. So PS is the load taken by steel, that is stress into area. PC is the load taken by the copper, stress into area, and that length X is unknown, so we calculate X value. So the X, the load, line of action of load should be 37.47. So this value should be 37.47. So the bar should be the total weight or the line of action of the load on this bar should be placed at a distance of X from this point A. So otherwise what happens, you can see here, if the load is suspended at the center of the rigid bar, suppose say the load you are applying on the rigid bar is at the center, what happens is that, so both steel wire and copper wire will carry the same load. So when you put the load at the center, what happens? The two wires should carry the same load. So when they carry the same load and the area is also same, the stress unit will be same. So that is not correct here. That will not satisfy the condition. So because the modulus of elasticity of both the wires is different, so that results in unequal elongation of the wires. So when you put the load at the center, here, so what happens? Since the stresses will be same, but modulus of elasticity is different, what happens is that because of this unequal elongation, so what happens? There will be elongation will not be same. So the elongation is not same. What happens? Then the bar starts rotating by some magnitude. So bar will get twisted. So that's why we put the load we can prevent that twisting of the load or the bar by offsetting the load. So we will not put the load at the center, but we will offset it by some distance so that the wires will elongate by same amount or by same quantity. Similarly, we have one more problem here. A load of 2 meganewton is applied on a column. So we have a column that it is a square column, and the column is reinforced with 4 steel bars of 12 mm diameter, one in each corner. So this is just like your house. Whenever you build houses or buildings, so we create or we build the columns. So in columns we have steel bars, and it is filled with concrete. So there you have to calculate the stresses in concrete and steel bar, and the Young's modulus of steel and concrete is given here. So first we will calculate the area of the steel bars. So there are 4 steel bars with cross-sectional area diameter or cross-sectional diameter of 12 mm. So 4 times area of, so there are 4 steel bars. So load will be taken by 4 bars. So that is 4 into area of each bar. Then area of concrete will be, this is covering the full area. So 500 minus area of the steel bars, that will give the area of the concrete. So area of the concrete is 500 by 500 mm. The column itself is 500 mm by 500 mm. So in that some area is covered by the steel bars and remaining area is covered by the column, that concrete. So if we add these two, that should be equal to this one. And we know these two equations. One equation is elongation should be same in both the elongation will be same in both the materials, steel and column concrete, and the load applied on total load applied on the column should be equal to sum of load on the steel and concrete. So by using these two equations, we will get the stress in concrete, that is sigma c. So sigma c, that is stress in concrete, will be 7.8 megapascal, and similarly stress in steel will be 15 times stress in concrete. So if you multiply this concrete stress into 15, you will get the stress in steel. So steel will take more load, as you can see here. So the stresses in the steel will be more than the concrete. So concrete and steel, when they are mixed together, it becomes a composite structure or a compound bar, or simply a column. In simple words, we call it as a column. So column, it's RCC. It's reinforced with steel. The concrete is reinforced with steel bars. So there are 4 steel bars. So each one will be having cross-sectional area so much, so into 4. And remaining area will be concrete here. So this square area minus this areas, that will give the area of the concrete. So like this, you have to analyze the composite or compound bars when the bar or the structure is made up of 2 different materials with 2 different cross-sectional areas and also different Young's modulus. So here you should remember these 2 equations. So we have one equation is that the strain or the elongation will be same in both the materials. Other condition is that the load applied on the column or on the bar will be shared by it will be shared by each members of the composite bars. Okay, that's it for the session. Thank you.